Welcome to this lesson on L-type and P-type smoothing filters used after rectifiers. We will begin with the meaning of ripple, examine why inductors and capacitors behave differently at DC and at ripple frequency, and then develop the L-type and P-type filters. Each derivation will state its assumptions before using the result. We will finish with worked examples, design checks, and a comparison of the two circuits. By the end of this lesson, you should be able to define ripple factor, identify the ripple frequency of half-wave and full-wave rectifiers, and explain the complementary actions of a series choke and a shunt capacitor. You will derive the small signal ripple response of an LC section, extend the reasoning to AC-LC pi filter, and use the results in numerical examples. You should also be able to recognize when an approximate equation is appropriate and list the practical checks required before choosing real components. A rectifier produces a unidirectional voltage, but that voltage is not perfectly constant. We separate it conceptually into a DC component, which supplies useful power to the load, and an AC component called ripple. Ripple factor is the RMS value of the AC ripple divided by the average, or DC, value. Because both numerator and denominator are voltages, ripple factor has no unit. A smaller ripple factor indicates a smoother output. Notice that the subscript R, RMS identifies the RMS value of the ripple alone, not the total RMS output. The total RMS output contains contributions from both the DC value and the AC ripple. Their squared RMS values add because the ripple has zero average over its period. Rearranging this relationship provides another way to calculate ripple factor when the total RMS and average values are known. This equation is useful in laboratory measurements and in analyzing rectifier waveforms. Keep the quantities distinct. VRMS is the RMS value of the complete output, VDC is the average value, and VRMS is the RMS value of only the alternating component. The filter must be designed for the frequency of the ripple, not merely for the supply frequency. A half-wave rectifier produces one output pulse per input cycle, so its dominant ripple frequency equals F. A full-wave rectifier produces two output pulses per cycle, so its ripple frequency is 2F. Angular ripple frequency, omega r, is 2 pi times Fr. At a 50 Hz supply, a full-wave rectifier therefore has a 100 Hz dominant ripple. This higher ripple frequency is easier to attenuate with a given inductance and capacitance. An inductor develops a voltage whenever its current changes. Its reactance is omega L, so reactance is 0 for ideal DC and increases directly with frequency. In a rectifier filter, the inductor is placed in series. It therefore offers little ideal opposition to the average load current, but considerable opposition to the alternating ripple current. A practical choke also has winding resistance and core limitations, which we will check later. The key point is that the inductor smooths current by resisting rapid change. A capacitor carries current whenever its voltage changes. Its reactance is 1 divided by omega C, so the reactance becomes smaller as frequency or capacitance increases. A shunt capacitor therefore provides a low impedance route for ripple current while behaving as an open circuit to DC in steady state. It also stores charge and supplies the load while the rectifier voltage is falling. The inductor and capacitor are complementary. The series inductor impedes ripple current, while the shunt capacitor diverts the remaining ripple away from the load. To estimate filter performance, we represent the full-wave rectified sine wave as a Fourier series. The first term, 2Vm divided by pi, is the DC component. The remaining cosine terms are ripple harmonics at 2 omega, 4 omega, 6 omega, and so on. A low-pass filter attenuates the higher frequency terms more strongly, so the first ripple harmonic at 2 omega normally dominates the filtered output. This dominant harmonic approximation gives a manageable and physically meaningful quick analysis. The DC component of the full-wave waveform is 2Vm over pi. The first ripple harmonic has a peak amplitude of 4 Vm over 3 pi, and its RMS value is that amplitude divided by √2. Dividing the first harmonic RMS ripple by the DC value gives approximately 0.471. The exact unfiltered full-wave ripple factor, including every harmonic, is about 0.482. We use 0.471 because our filter model retains only the dominant harmonic, while recognizing that it is an approximation. This is the L-type, or LC, smoothing filter. The inductor is connected in series between the rectifier and the load. The capacitor is connected in parallel with the load resistance. The arrangement resembles the letter L. As rectifier current rises, the choke stores magnetic energy. As the rectifier voltage falls, it releases energy and helps maintain current. The capacitor charges when output voltage rises and supplies the load when output voltage falls. Together they reduce both current and voltage variation. Both reactive components store energy. The magnetic energy in the inductor is 1/2 Li squared. The electric energy in the capacitor is 1/2 CV squared. During portions of the rectifier cycle, these stored energies are returned to the circuit and help maintain load current and voltage. This is why the output changes more slowly than the unfiltered waveform. The filter does not generate additional power, it redistributes energy in time. Real components dissipate some energy through winding resistance, capacitor equivalent series resistance, core loss, and dielectric loss. We now analyze only the AC ripple component. At ripple angular frequency omega, the series inductor has impedance J omega L. At the output, the capacitor is in parallel with the load resistance. Combining those two parallel impedances gives RL divided by 1 plus J omega RL times C. This equivalent impedance is called ZP. Separating DC and ripple in this way is a small signal method. The DC value establishes the operating point, while the AC equivalent circuit predicts how much ripple reaches the load. The ripple transfer function is output ripple divided by input ripple. Applying the voltage divider relation gives ZP divided by the sum of J omega L and ZP. After substituting the parallel impedance and simplifying, we obtain a second-order low-pass response. The real term contains 1 minus omega squared LC. The imaginary term contains omega L divided by RL. The load therefore affects the damping. This expression is more informative than an unloaded reactance ratio because it shows both resonance and load dependence. Taking the magnitude of the complex transfer function gives the exact attenuation for this idealized loaded network. The first squared term describes the reactive frequency response, and the second squared term includes load damping. The ideal undamped resonance occurs at omega 0 equal to 1 divided by √LC. Near resonance, a lightly loaded LC network can amplify rather than attenuate a component. A smoothing filter should therefore operate with its dominant ripple frequency well above resonance and with enough damping to prevent an excessive peak. For a well-designed smoothing filter, the ripple frequency is far above the LC resonant frequency. Then omega R squared LC is much greater than 1. If the damping term is also not dominant, the magnitude simplifies to 1 divided by omega R squared LC. This reveals the design trend directly: increasing L, increasing C, or increasing ripple frequency reduces the transmitted ripple. It also explains why full-wave rectification is easier to smooth than half-wave rectification at the same supply frequency. The output ripple factor is approximately the dominant input ripple ratio multiplied by the filter magnitude at the ripple frequency. Substituting 2 divided by 3√2 for the dominant input ripple ratio gives the first boxed expression. This form is preferred because it uses omega R directly and avoids ambiguity. For a full-wave rectifier, omega R is twice the supply angular frequency omega. Substitution gives root 2 divided by 12 omega squared LC. Both formulas are approximations based on the dominant harmonic and the high attenuation condition. In the first example, a 50 Hz full-wave rectifier supplies a 1 kΩ load through an LC filter having 10 henries and 20 microfarads. Because the rectifier is full-wave, the ripple frequency is 100 Hz. Multiplying by 2 pi gives an angular ripple frequency of approximately 628.3 radians per second. Establishing the correct ripple frequency is essential. Using 50 Hz here would produce an incorrect attenuation and a ripple estimate for times too large in the high-frequency approximation. We first calculate the two-dimensionless terms in the exact magnitude equation. Omega r squared LC is 78.96, confirming that it is much greater than 1. The damping term omega RL divided by RL is 6.283. Substitution gives a filter magnitude of 0.01278. Multiplying by the dominant input ripple ratio, 0.4714, gives an estimated output ripple factor of 0.00602, or 0.602%. The high attenuation approximation replaces the complete denominator by omega r squared LC. Its magnitude is 1 divided by 78.96, or 0.01266. Multiplying by the same dominant input ripple ratio gives 0.597%. This is very close to the exact ideal network result of 0.602%. The agreement confirms that the simplifying condition is suitable for this example. It does not mean that either result includes practical winding resistance, capacitor loss, diode resistance, or transformer impedance. The approximate L-type formula can be rearranged for preliminary selection. A specified maximum ripple factor establishes the minimum product LC. If a suitable choke value is chosen first, the third equation gives the minimum capacitance. These are starting values, not final component selections. After choosing standard values, the designer must calculate the exact loaded response, check resonance and damping, allow for tolerances and winding resistance, and confirm current, voltage, temperature, and transient ratings. This is the pi-type, or CLC, filter from the corrected source document. Capacitor C1 is connected directly across the rectifier output. It charges near the voltage peaks and provides the first stage of smoothing. The series choke then opposes the remaining ripple current. Capacitor C2 diverts the residual ripple away from the load. The arrangement resembles the Greek letter pi. It normally produces a higher DC voltage and lower ripple than a single LC section, but the first capacitor creates short, high charging current pulses in the diodes and transformer. The first capacitor recharges rapidly near each rectifier peak and supplies an approximately constant load current between peaks. From I equals C delta V over delta T, the peak-to-peak voltage change is approximately I sub L divided by F sub RC1. If the small ripple is treated as triangular or sawtooth, its RMS value is the peak-to-peak value divided by 2√3. This model ignores the finite charging interval and source impedance, so it is most useful as a preliminary approximation rather than an exact prediction. Replacing load current by VDC divided by RL and dividing the RMS ripple by VDC gives the first stage ripple factor. It decreases when ripple frequency, load resistance, or input capacitance increases. For a full-wave rectifier, FR equals 2F, producing the boxed expression with √3 in the denominator. A heavier load means a smaller RL and therefore larger ripple, because the capacitor discharges more rapidly between charging peaks. After the first capacitor, the choke and output capacitor form another loaded LC low-pass section. Its exact ideal magnitude is the same expression derived earlier, with C replaced by C2. When omega r squared LC2 is much greater than 1, the attenuation becomes approximately 1 divided by that product. This step treats the pi filter as two cascaded smoothing actions. It is convenient for initial design, but the stages are not perfectly independent because the rectifier charging process and source impedance influence the waveform at C1. The estimated pi filter ripple factor equals the first stage ripple factor multiplied by the attenuation of the LC2 section. Substituting the two approximations produces the first boxed equation written in terms of ripple frequency and angular ripple frequency. For a four-wave rectifier, Fr equals 2f and omega r equals 4 pi f, producing the second boxed form. This cascade formula shows that both capacitors and the choke contribute to smoothing. The pi filter example uses a 50 Hz full-wave rectifier, a 1 kΩ load, 40 microfarads at the input, a 10 Henry choke, and 20 microfarads at the output. Substituting F, RL, and C1 into the full-wave capacitor input formula gives a first-stage ripple factor of 0.07217. This is approximately 7.22% before the choke and second capacitor provide their additional attenuation. At 100 Hz ripple frequency, omega r is 628.3 radians per second. The LC2 section attenuation is approximately 0.01266. Multiplying this by the first stage ripple factor gives 9.14 times 10 to the minus 4, or 0.0914%. If the DC output is 20 volts, multiplying by the ripple factor gives an estimated RMS ripple of 18.3 millivolts. This very low value illustrates the stronger smoothing available from a pi filter. The L-type filter is attractive when load current is higher and regulation is important. With continuous choke current, rectifier peak current is generally more moderate. The pi filter normally gives lower ripple and a relatively high DC output because C1 charges near the rectified peak. The cost is higher charging current stress in the diodes and transformer and generally poorer voltage regulation as load changes. Both designs may require a physically large and expensive choke. The correct choice depends on the required output voltage, load current, ripple, regulation, size, and cost. Practical design begins by checking the LC resonant frequency. The operating ripple frequency should be well above F0, and the network must have adequate damping. The choke current rating must exceed the DC load current, including allowance for ripple and transients, and its core must not saturate. Copper loss equals IRMS squared times winding resistance. Capacitors require adequate voltage margin, ripple current rating, temperature rating, equivalent series resistance, lifetime, and correct polarity. In a pi filter, C1 usually experiences the greatest charging current stress. Choke input operation requires sufficient load current to keep choke current nearly continuous. At very light load, conduction can become discontinuous and the output voltage may rise. A bleeder resistor can establish a minimum load, but it continuously wastes power. In a pi filter, the input capacitor produces large charging pulses, so verify diode surge current, repetitive current, peak inverse voltage, transformer heating, and fuse selection. Filter capacitors can retain dangerous energy after the supply is switched off. Use discharge resistors and verify that voltage is safe before touching the circuit. A reliable design process begins with output voltage, load current, frequency, permitted ripple, regulation, and transient requirements. Calculate the equivalent load resistance. Choose the topology according to whether regulation and moderate rectifier current, or higher DC voltage and lower ripple, has priority. Use the approximate equations to obtain initial component values. Then check resonance, damping, light load behavior, component ratings, tolerances, and losses. Recalculate with non-ideal values, select standard components, simulate the complete rectifier, and finally verify the design by safe laboratory measurement. 5 misconceptions are worth correcting. First, a finite capacitor reduces ripple but cannot remove all AC. Second, increasing capacitance can also increase surge current, transformer heating, size, and cost. Third, an ideal inductor passes DC while opposing changing current. Fourth, the ripple equations derived here depend on assumptions about the waveform, loading, and dominant harmonic. They are not exact complete rectifier models. Fifth, half-wave and full-wave circuits have different ripple frequencies, and that difference strongly affects the required filter values. To conclude, ripple factor compares the RMS AC ripple with the DC output. Full-wave rectification produces dominant ripple at twice the supply frequency. An L-type filter uses a series choke and shunt capacitor, with high-frequency attenuation approximately proportional to 1 divided by omega sub R squared LC. A pi filter adds an input capacitor and therefore gives stronger smoothing, but creates larger charging current peaks and different regulation behavior. Approximate equations guide initial selection. Final designs require non-ideal analysis, ratings, simulation, measurement, and safe handling. Thank you.